Okay, I'd like to welcome everybody to another edition of Quantum Fluids and Isolation. So today I'm very happy to be introducing Dr. Shafayat Hossain. So Dr. Hossain got his bachelor's degree in electrical engineering from the Bangladesh University of Engineering and Technology in 2013, his master's in electrical engineering from Princeton in 2016, his PhD in electrical engineering from Princeton in 2019, and he's currently a postdoc in Professor Shafayat Hossain's lab in Princeton. He's been a recipient of many awards, including the Institute of Complex Adaptive Matters Quant MX Scientific Exchange Awards 3 times, 2016, 2017, 2018. And he was the recipient of Princeton University School of Engineering and Applied Science Travel Grants 2016, 2018, 2019. And today he'll be talking about spontaneous Valley and spin polarization of electrons at zero magnetic field. So please help me in welcoming, either by muting yourselves and clapping or by clapping virtually, Dr. Shafayat Hossain.
Thank you, Joshua, for the introduction. So, a little bit about myself. So, I graduated in 2020. So, just 5 months ago. I worked with Mansoor Shaigan, and so today I will be discussing some of my PhD work. And now, I work with Professor Hossain. So, before I used to do quantum transport experiments. Now I'm kind of focusing on spectroscopy side of things, doing scanning tunneling microscopy and also some optics, near field optics. So with that, welcome everyone. So the topic of today's talk would be spontaneous Valley and spin polarization of electrons at zero magnetic field. So before starting this long talk, I want to convey the key takeaways. So we start with a 2D electron system where the electrons have 2 degrees of freedom. So they have spins and they have 2 valleys. And just to note that the valleys are the local minima in the electronic band structure. At high densities, we find that the electrons occupy both 2 spins and 2 valleys. However, if we start lowering the densities at sufficiently low densities, what happens is electrons spontaneously transfer to one of the valleys and becoming valley polarized. Now, as we lower the density even further, the electrons finally become fully spin polarized. So the electrons start with 2 degrees of freedom, both spin and valley. However, they start losing both degrees of freedom and becoming fully spin and fully valley polarized if you lower the density sufficiently. On the other hand, there is another set of phase transition that goes on as we change the electronic density. So at high electronic density, the electron system behaves as a metallic system. However, if we start lowering its density below a certain density, the system becomes insulator. And finally, at extremely low densities, the electrons crystallize and form a Wigner solid at very low densities. So I will discuss all these transitions, and all these transitions occur thanks to the electron-electron interaction. All right. So here would be the outline of the talk. I'll be talking about what happens when you lower the electron density. So let's start with what happens really between the electron-electron interaction at very low densities. And then I will introduce our material platform and then discuss our experimental data. So let's start with a very classic example, a textbook problem. So electrons in a box. Electrons have kinetic energy even at 0 temperature, and that kinetic energy is simply the Fermi energy. Now let's make this box 2D. And in 2D, the specialty is the density of states is constant. So the kinetic energy, or the Fermi energy in this case, just goes as N or 1 over R squared, where R is the average inter-electron spacing. Now, these electrons also interact with one another via Coulomb repulsion. And this Coulomb repulsion goes as 1 over R. Now, the ratio of Coulomb interaction to the kinetic energy now, it's just goes as R, which is 1 over square root of n. So what does it mean? It means that the lower the density, the higher the ratio of the Coulomb interaction to the kinetic energy. So in other words, if you lower the density of an electron system, a 2D electron system, the stronger the electron-electron interaction will be. So the dilute the system, the more interacting it is. It's kind of surprising that just by lowering the electron density, you can make a system interacting. Now, there is another energy scale, which is inevitably present and percentage-wise gets more prominent at low densities, which is the disorder. So this disorder actually competes with the interaction and wants to trap the electrons at random sites. So to see the impact of this electron-electron interaction at low densities, one needs to keep the disorder low. So we need to have a clean sample. And an example of a clean 2D electron system would be a modulation-doped gallium arsenide quantum well. Here you have the dopants that is spatially separated from the quantum well. And because of this modulation doping, the 2D electron system is formed inside the quantum well. And one can get very high mobilities, electron mobilities in these systems of the order of 10 million centimeters squared per volt second. Okay, so now what do we expect to see from a low density electron system? So back in 1929, Felix Bloch wrote a paper describing a magnet that's driven by interaction, the so-called Bloch ferromagnet. So it happens at very low densities. So the basic idea is very simple. Electrons can lower their Coulomb energy just by aligning their spins. In that way, the electrons will be spatially pushed apart and the Coulomb energy would be minimized. On the other hand, electron can also lower their kinetic energy or the Fermi energy just by putting 2 electrons in each momentum state. So to do that, thanks to the Pauli exclusion principle, the system has to be paramagnetic because these 2 electrons have opposite spins. So now we see that the Coulomb energy or the electron-electron interaction favors the formation of a ferromagnetic state, whereas the kinetic energy favors the formation of a paramagnetic state. And as I just described a few slides ago, if you lower the density sufficiently, at some point, this Coulomb interaction wins. It becomes stronger than the kinetic energy. So electrons will favor to reduce their Coulomb energy instead of the kinetic energy, and the system should become a ferromagnet. So that's what's called a Bloch ferromagnet. Now the question is, how low of a density do we need to see such a ferromagnetic state? So the requirement can be expressed conveniently using a parameter called RS. So this RS is again the same ratio, the ratio of Coulomb energy to the kinetic energy, and it goes as 1 over square root of n. So the lower the density, the higher the RS. So according to a Monte Carlo calculation by Attaccaliti back in 2002, if you have small RS, so RS less than 26, the 2D electron system should be a paramagnet. Now, if you raise the RS to above 26, the system should become a ferromagnet, so which is the Bloch ferromagnet. And if you raise the RS to extremely high values, such as greater than 35 here, the system should finally freeze into a Wigner solid. Now, what does these RS numbers mean in terms of density? So to give an example, let's assume a typical gallium arsenide 2D electron system where the electron mass is 0.067 times free electron mass and the dielectric constant is 13. So RS equals to 26, which is required to see this ferromagnet, entails a density of 4.6 times 10 to the power 8 per centimeter squared. It's very low. And almost impossible to realize in a practical system, in a practical gallium arsenide system. So this is perhaps why there has been no unambiguous experiment to probe such high values of RS. Now, so what?
Shafayat,
Yes.
I had Sandeep Joy has one question in the chat.
Yes. Yes. Go
Is
ahead.
Bloch ferromagnet, is it still a Fermi liquid?
Yes, it is still a Fermi liquid. Yeah.
Okay, thank you.
Mm-hmm. Yeah. Okay. So of course then. Okay. So with gallium arsenide system, then we cannot reach such large values of RS. So we need a different material platform. So to do that, to realize such large values of RS, we use aluminum arsenide. So before again going to the details, let's focus on two parameters, the electron effective mass. So the electron effective mass in this system is 0.46 times free electron mass. And the second parameter is the dielectric constant, which is 10, as opposed to 13 for the gallium arsenide. And in the effective mass is about a factor of 8 larger than the electron mass in gallium arsenide. So why are these two important? Because we see that RS goes as m star divided by the dielectric constant. Now, in this case, since the mass is larger and the dielectric constant is smaller, we can attain large values of RS. So in this case, RS equals to 26 means a density of 3.5 times 10 to the power 10 per square centimeter. So which is attainable in a physical system. Okay, so now to some of the details. So here you see the first Brillouin zone of aluminum arsenide, and electrons occupy 6 half ellipsoids or 3 full ellipsoids in the first Brillouin zone, and they are all in the X point. So in this system, there are 3 conduction band valleys. And another interesting thing is these valleys are anisotropic. You see, those are ellipsoid, not a circle in a gamma point, as in the case of gallium arsenide. And the mass anisotropy in this system is a factor of 5. So just to do a lighthearted illustration for the valleys, it's kind of like a local minima between 2 mountains. So as similar to these clouds, electrons can also accumulate in the valley. So it's just like a local minima in the conduction band for the electronic system. Now, the valley occupation in aluminum arsenide quantum wells is very interesting. So as in bulk that I just described, you have 3 conduction band valleys. However, when the aluminum arsenide is grown as a quantum well, the valley degeneracy is split. It's because the aluminum arsenide quantum well is grown on top of a gallium arsenide wafer. And then what happens is if you grow along a Z direction, so then this Z valley, which is the 001 direction valley, has larger effective mass along the direction of the confinement. So again, from the energy levels of the quantum well, in that case, one should expect this Z valley should be occupied all the time. And this is indeed the case for narrow quantum wells. Now, what happens is, again, the aluminum arsenide is grown on top of gallium arsenide. So there is a slight lattice mismatch. And the slightly smaller lattice constant of gallium arsenide will cause a biaxial compression on the in-plane atoms of aluminum arsenide. And it will cause a lowering of the conduction band of the X and Y valleys with respect to the Z valley. So finally, if the well width is larger than 6 nanometer, what happens is instead of this Z, only 2 in-plane X and Y valleys become occupied if a wide quantum well is grown out of aluminum arsenide. Now, this is the case for our sample. So we use a 21 nanometer wide aluminum arsenide quantum well. And in this case, without any external strain, electrons occupy two in-plane values, X and Y. And these two values are degenerate. And the sample is grown by Lauren Pfeiffer's group at Princeton using molecular beam epitaxy. All right. So now, as I discussed, electrons in aluminum arsenide occupy two in-plane valleys without any external strain. Now, we can control this valley occupancy just by applying that external strain. So how do we do that? We take the sample, glue the sample on top of a piezo actuator, and then just by applying a voltage bias across this piezo actuator, we can apply a strain to the sample and then tune the valley occupancy. So this valley tuning can be well presented just by a resistance measurement as a function of piezo bias or strain. So here I'm showing the resistances measured along 100 and 010 direction. So the 100 is along the long axis of the X valley, and 010 is along the long axis of the Y valley. So now let's start from this point B, the middle one, where these two resistances, the R100, the black one, and R010, the red one, are same. So at this point B, we call it a balance point, which occurs at 0 strain. And then if we apply external strain, for example, go apply negative values of strain, we see that the black trace goes up while the red trace goes down. So the resistance along 100 increases while the resistance along 010 decreases. What's the reason? It's because at negative strain, electrons move to X valley, and X valley has larger effective mass along 100 direction, as you can see from the long axis of the X ellipsoid. So since it has a larger effective mass, which means lower electron mobility, which means a larger resistance. And opposite happens for the 010 direction, because again, in 010 direction, X valley has smaller effective mass, so larger mobility, and consequently smaller resistance. And so finally, after applying strain, we end up in this point A, where electrons only occupy X valley, and then the resistance ratio between these two directions, the anisotropy, becomes slightly more than a factor of 3. And the top panel shows the density of state diagram. For example, in point B, X and Y are degenerate, but that degeneracy is lifted and electrons end up in X valley if we apply negative strain. And on the other hand, if we apply positive strain, exactly opposite thing happens. So this red resistance curve goes up while the black resistance curve goes down. And this is because, again, this Y valley has a smaller mass along 100 direction, which should result in a smaller resistance. So just by applying a piezo voltage, we can tune the valley occupancy in the system. We can have X valley, we can have degenerate condition, and we can have Y valley occupied. All right. So now I described our material platform. Let's go to our experimental data. And we start with the first case. So again, at high density, we start with a situation where electrons occupy both X and Y, because we keep the strain at 0, where X and Y are degenerate. And then we start lowering the density just by applying a gate voltage. And we find that below a critical density NV, electrons spontaneously transfer to the Y valley. All right, so let's look at our experimental data. So here we are also measuring the same thing, the resistances along 1, 0, 0 and 0, 1, 0 directions. And we are measuring these resistances as a function of density. So we apply the gate voltage and tune the density and just measure the resistance. So let's start from the high density. So at high density, for example, at 12 times 10 to the power 10 per square centimeter, these black and red traces are nearly equal. And you would expect that because at zero strain, the values should be degenerate. Now we start lowering the density. And finally, as we lower the density below 6.3 here, we find that these two traces split up, and the black trace starts to go down and the red trace goes up, and then they finally keep an offset with each other and goes on as the density is further lowered. And here is a zoomed in version of this splitting up. So, so what is happening? So what's happening is here, if you see the red trace or R010 is becoming nearly a factor of 3 or even slightly larger compared to R100, which is consistent with valley occupancy in the Y valley. Because again, just to remind you, Y valley has a larger effective mass along 010 direction, and X valley has a smaller effective mass along 100 direction. So the black resistance or R100 should be smaller compared to the red resistance trace, the R010. So this splitting up signals splitting of the valley degeneracy at low densities. Again, just to remind you of the introduction that Felix Bloch predicted that for a system with two spins, there is a transition from a paramagnetic to a ferromagnetic state. So the electrons from two spins suddenly go to one spin. So this is kind of analogous to what Bloch predicted, but for valleys. So we start with a two valley system and then finally end up having only one valley occupancy. So our observation can be akin to the Bloch ferromagnetism for valleys. And just to note that the density where we observe this transition, it's 6.3 times 10 to the power 10 per square centimeter, which corresponds to RS of about 20. Okay, so let's look at the data a little more and look at the temperature dependence. So as we raise the temperature, as you can see, the transition here, or the splitting up of these two resistances, is clear even at 1 Kelvin, but starting from 1.2 Kelvin and higher temperatures, these black and red traces again coincide. So this splitting is not visible anymore. And if we summarize the data in here as the temperature and function of density, and we plot the anisotropy R010 divided by R100 at low densities below 6.3 times 10 to the power 10. And at lower temperatures below 1.2 Kelvin, the system is anisotropic in a way that signals the Y valley occupancy. But in all other cases, the system is isotropic throughout. So again, just to summarize here, that this transition signals the occupation of Y valley as we lower the density.
So there's one question in the chat.
Yes.
Does the valley polarization always prefer Y valley, or does it vary from sample to sample?
Great question. Yeah, thank you. So we tested two samples. For both cases, we found Y valley. So I don't know why it favors Y valley, why not X valley? But yeah, we tested two samples of two different wafers, and we still found Y valley. Yeah, probably we need to test even more samples to kind of get a statistical data on, say, how many samples favor X, how many samples favor Y. But so far, we have only seen Y.
Yeah. Thank you.
Yeah, thanks. All right. Now, a natural question is, what happens if we forcefully valley polarize the system at the beginning? Because we can just apply strain and then valley polarize the system to start with. So we do that here. So we apply a large negative strain, put all the electrons in X valley to start with. So see, the black resistance is now larger than the red one. And then we start lowering the density. And of course, we don't see any transition. And then we can do the opposite thing, put all the electrons in Y valley to begin with, and then lower the density. Again, no transition happens. The two resistances maintain a similar anisotropy throughout the density. So no transition happens when the electrons already begin with a valley polarized case. So this transition that we see below 6.3 only happens when we start with a valley degenerate system at high densities, and we lower it, and then all the electrons end up in Y valley. Okay. So just to conclude again, so as we lower the density, electrons seem to get rid of their valley degree of freedom below 6.3. Now towards the spin, and let's see what happens. Yes, go ahead.
Can you go to the previous slide?
Yes.
So if the spontaneous valley polarization is a first order transition, then even in the presence of this strain, there should be some transition at a lower density, isn't it?
The question is, then when the system is already valley polarized, should there be a transition?
Yeah.
So you can imagine if the transition is due to the, say, inter-valley exchange interaction, again, say, akin to Bloch spin ferromagnetism, that's again stem from the exchange interaction between the spins. So if it stems from the exchange interaction between the valleys, then you need to have two valleys to see that transition. So if we already start with one valley, be it X or Y, and start lowering the density, there is no other valley, or the other valley energy level is too far away. As you can see, for example, here, if it's too far away, then yeah, there should not be any transition in my understanding. So does that, yeah.
What if the temperature is raised? Like what if the temperature is increased? Can you see the transition then?
So in this case, right?
Yeah, in this case.
Yeah, so I guess if you raise the temperature, you kind of again put some electron in the other valley because of just the Fermi function broadening.
Yeah.
Good question. So there is a technical caveat. So let me go back. So the temperature dependence, all those things that you have seen here, those are done at zero strain. Mm-hmm. As I discussed, those are all at zero strain. So if we are to do this at high values of strain, then that means that we need to apply a very large piezo bias and then do this experiment, which is tricky because the piezo cannot survive high temperatures, still maintaining that large bias. Okay. So we know that we can do this up to 500 millikelvin or so, but that's all we can with the piezo with high bias. Yeah, because if you just let me go back. Yeah, here it may be good. Yeah, so you see the voltage levels in this case. So if we are to apply, say, go here and then apply 600 or minus 600 volts. So this is minus 0.6 kilovolt. That's huge. And it won't withstand the high temperature and high voltage. So to
Okay.
do that, we need low temperatures.
Okay, thanks.
Yeah, that's a great question. Yeah, thank you. All right. Okay. Yeah, so let's see what happens to the spin degree of freedom and as we go to even lower densities. So just to give the summary before we go to the details. So the 2D electron system start with a paramagnetic, being paramagnetic at high densities. And again, we do the same exercise, lower the electron density. We find that below a sufficiently low density, the systems becomes fully spin polarized. So to probe this spin polarization, we measure magnetizing field called BM. So how do we measure this magnetizing field? So again, we are measuring resistance, for example, here R100 as a function of a parallel magnetic field. And what happens is, if you see here, the resistance goes up as a function of parallel magnetic field, and then finally saturates. So why does this happen? Because as we apply the parallel magnetic field, it adds a Zeeman energy, which increases the spin polarization of the system. So we know that electron of one spin screens the electron of the opposite spins from the impurity potential. So the resistance is low. But as you increase the polarization, electrons will lose that screening, and therefore the resistance will go up. And finally, the resistance will saturate, and it kind of becomes flat. The reason is beyond this magnetic field, which we call magnetizing field, the polarization is already maximized, and there is no further change in polarization, so no further change in screening, and therefore no change in the resistance. So from this magnetizing field BM, we can easily calculate the spin susceptibility of the system. So because at this point, the Zeeman energy is just the Fermi energy of the system. So from that, we can calculate the spin susceptibility of the system, which just goes as N over Bm. Okay, so this is also a very well-established technique. So we do this experiment, measure resistance as a function of parallel magnetic field, and we do that for different densities. So starting from the high densities, we see that it shows the expected behavior. So at high parallel magnetic field in both negative and positive sides, the resistance nearly saturates. And we mark this magnetizing field with this downward arrow. Now, the first thing that catches the eye is this magnetizing field is getting decreased, getting lower and lower as we lower the density. And which also means, since magnetizing field is, spin susceptibility is just N over Bm, so the spin susceptibility is going up as we lower the density. So importantly, if we lower the density below this 2.1 and come to 2, it seems nearly flat. So the resistances seem nearly flat. Again, the question is why? The obvious explanation would be because there is no change in screening as a function of parallel magnetic field. The resistance should stay flat. And why does that happen? Because the system is already fully spin polarized at 0 parallel magnetic field. So there is no further change in polarization or screening as we apply more and more parallel magnetic field. So, and this happens, vanishing magnetizing field happens at a density of 2, which corresponds to RS of 34.5. So again, to summarize the data, we plot this magnetizing field as a function of electron density. And this magnetizing field comes down as we lower the density and finally goes to 0 at a density of 2 times 10 to the power 10 per square centimeter, which corresponds to RS of 34.5. And if we also plot the spin susceptibility of the system, since spin susceptibility is just N over Bm, it diverges below this 2 times 10 to the power 10 per square centimeter density. So to conclude that as we again lower the density below a certain value, the electrons become fully spin polarized. And it appears to be highly reminiscent of Bloch ferromagnetism, but I will come back to it a little later. So let's first discuss the data a little bit. So here we're showing 2 traces, black and red, for 2 different sweep direction. The black one is from negative to positive, and the red one is from positive to negative direction. And close to this transition, spin transition, there is noticeable hysteresis. And when we also look at the resistance as a function of perpendicular magnetic field, we find similar hysteresis close to the densities where the spin transition happens, for example, at 2.2 or 2.1, 2, and even below the spin transition density. However, at high densities, for example, at 2.5, there is no noticeable hysteresis present. And the same hysteresis is also observed in Hall resistances, again, close to the spin transition density, which is 2, and below, for example, 1.7. And at higher density, for example, 2.5, there is no hysteresis visible. So this hysteresis is usually seen in ferromagnets, and it signifies the formation of magnetic domains when the spin orientation switches due to the applied field. So this suggests the formation of a ferromagnetic phase below the transition. So one other thing, I will get back to it a little later, we also observe integer quantum Hall effects at the filling factor 1. We observe resistance minima in the Rx, this longitudinal resistance, and plateau, well quantized plateau at a Hall resistance down to very low densities. I'll come back to it a little later. So it's very tempting to interpret the spin transition data as a Bloch transition too. However, there is a very important caveat. Bloch's original prediction was for a metal. However, at the density where we observe this spin polarization, for example, in here too, the system is already insulated. So let's have a look at the data. So here we are showing the resistance as a function of temperature. So at high densities, for example, 5 times 10 to the power 10 per square centimeter here, the resistance comes down as we lower the temperature, which means the system is a metallic system. But I mean, this trend continues down to this 3.2. However, if we go to even lower densities, this trend reverses. So the resistance starts to go up as we lower the temperature, which is consistent to an insulating transport. And by the time we reach the spin transition at 2 times 10 to the power 10 per square centimeter, the system is already clearly insulating. So the ferromagnet that we see is likely not a Bloch ferromagnet because we observe it in an insulator. One other thing I want to point out is the spin transition density, which is 2, is the smallest one. And then at a slightly higher density, there is this metal-insulator transition, for example, at 3.2. And as I described before, the valley transition density is slightly higher, which was around 6.3. So there is a nice cascade of transition going on as a function of density. So now let's get back to the magnetotransport data that I showed a couple of slides earlier, up to nu equals to 1. So we also see a signature of fractional quantum Hall effect down to very low densities. So even below the spin transition density, which was 2, we observe clear resistance minima at filling factor 1/3 and accompanied by quantized Hall plateau at 1/3, and the plateau corresponds to 3h/e squared. So the presence of this fractional quantum Hall effect down to very low densities signifies the presence of electron-electron interaction in the system. So again, the ferromagnetic transition that we observe at very low densities should be influenced by interaction. So again, this sounds a lot like a Bloch ferromagnetism, interaction-driven ferromagnetism, except that the transport at zero magnetic field is insulating. So maybe the ferromagnetic state that we observe is a ferromagnetic correlated insulator. All right. So a quick summary up to now is we start with a valley degenerate and a paramagnetic system. So electrons have 2 degrees of freedom at high densities, but they finally end up losing both. So first, the system becomes valley polarized, and then finally, the systems become fully spin polarized. Now, also there is another set of transition, because the system is metallic down to 3.2, but it becomes insulating. And then I'll come back to what happens if we go to even lower densities. Now, a couple of important points. The valley transition that we observe occurs in a metallic system. So the system is still metallic. So the valley polarization transition can be a valley analog of Bloch ferromagnetism. But for the spin case, since this happens when the system is already insulating, it may not be a Bloch ferromagnet, it may be just a correlated ferromagnetic insulator. Now, you may ask why the threshold density or the critical density for this valley polarization transition is larger than the spin polarization transition. The answer is, I don't know. That's a good food for thought. Okay.
So Shafayat, now this is one question from Sandeep Joy in the chat. What is the nature of the insulating state? Is it a Wigner crystal?
Good question. The insulating state that I just showed below 3.2, at these densities, it's likely not a Wigner crystal, but at very low densities, yes. I will describe it right away, basically, what happens to very low densities. Yeah, but at high densities, for example, let's say in here, it's not a Wigner crystal. There are a couple of explanations I heard from Professor Kivelson from Stanford. He thinks it can be a Wigner glass, or it can be a microemulsion phase. But again, our experiment cannot really prove or disprove that. So yeah, does that answer your question?
Yes, thanks.
Okay, yeah, thank you. All right. So the final part, what happens if we go to very low densities? Again, starting from a Wigner crystal, we would expect if you have a perfect Wigner solid, that would slide, and it should not show a strongly insulating transport. But in a realistic system, such as in gallium arsenide 2D electrons in high magnetic fields, people observe pinned Wigner solid, which is pinned by the ubiquitous disorder potential. And a piece of evidence for the pinned Wigner solid is a nonlinear response as a function of applied DC bias. So to that end, we measured the differential resistance as a function of DC bias. And starting from the high density cases, for example, 2.5, where I've shown you that the system is already insulating, and we observe pretty linear response, linear differential resistance as a function of DC bias current, at least in this range. Now, as we keep lowering the density, starting from, you see this light blue trace, 1.8, looks like the differential resistance is showing some nonlinearity as at small DC biases. Finally, from 1.7, we start to observe strong nonlinearity at small DC bias, and it goes stronger and stronger as we lower the density, say down to 1.2. So what can be the reason behind this nonlinearity? So we know that at zero bias, Wigner solid is being pinned by the ubiquitous disorder potential. So we expect a large differential resistance. But above a small DC bias, which is also known as the conduction threshold, the Wigner solid gets depinned. And then what should happen is the differential resistance should fall rather sharply. And again, in case you were wondering about the presence of large noise for the large DC biases in this range, it's somewhat associated with the broadband noise that comes from the domain wall motion of this unpinned Wigner solid. So the differential resistance as a function of DC bias data is consistent with a Wigner solid formation below a density of 1.8 or 1.7 and down to very low densities. Yeah, but above that density, from the differential resistance measurement, we think it's not a Wigner solid. So the Wigner solid threshold, we associate it to the density of around 1.7, so which again corresponds to a RS of 37. So one other important thing that I want to point out is this Wigner solid that we observe. We observe when the 2D electron system is already a ferromagnet. So this Wigner solid is likely a ferromagnetic Wigner solid. But in future, we are planning to do more measurement on this Wigner solid phase. Also, one goal is to determine the lattice shape of this Wigner solid, because there are some theoretical predictions that if you have a mass anisotropy in the system, such as in ours, we have a factor of 5 mass anisotropy, it should result in a rectangular Wigner solid. So the Wigner solid that I'm showing is just a triangular. So this might not be correct. So more measurements are underway. Okay. So with that, I think I can conclude my talk. So first, I would like to acknowledge all the help and support from Shigan Lab. And the samples came from Lauren Pfeiffer's group, who was our right next door. And then also I would like to acknowledge lots of help and support from Steve Kivelson and Janandra Jain. They gave a lot of theoretical support. And I would also like to thank the funding agencies who supported our work. So with that, I would like to conclude my talk. Yeah, thank you. I would be happy to take questions. Thank you.
Very nice talk. So I had 1 or 2 questions. Maybe at first, the audience can ask some questions.
Yeah, great talk. I have few questions. Can I?
Mm-hmm. Go ahead.
Have you done a measurement on the Wigner solid phase about the magnetization, or are you proposing that it's a ferromagnetic solid?
Good question. So let's go back to the data. Yes. So if you see our resistance as a function of parallel magnetic field data, it's flat. It's reasonably flat at very low densities even. So for example, 1.3, where the system already shows strong nonlinearity in differential resistance. So we think that's the Wigner solid. And at that density, there is no parallel field dependence in the resistance. So this is again consistent to a full spin polarization. So we think that
But
since there is no magnetizing field, it should be a ferromagnetic Wigner solid.
I mean, if
Yes.
if the transport is mediated by a spin, like sliding of the spin to Wigner solid, it would be insensitive to the spin orientation of the individual electrons. So why would you how do you corroborate these two? Like, do you get
that's a great question. So again, before answering that, let me first tell you. So as at very low densities, such as this, a direct measurement of magnetization as the magnetometry is extremely difficult. So again, for us, we cannot really measure magnetic moment directly for such a low density system. And then the way that we do, again, determine the say the presence of ferromagnetism or the magnetism in the system would be just by resistance as a function of parallel field. So with that, again, we cannot really distinguish whether the insensitivity to the parallel field is coming from another effect or not. So again, that's a limitation of the technique. So if because of the sliding, as you mentioned, it becomes insensitive to the magnetic field, then there is no way for us to distinguish that. But again, I'm not 100% certain that if you have a unpinned sliding Wigner solid, that's completely insensitive to the large parallel magnetic field.
Mm-hmm.
Yeah, but again, if it is insensitive indeed, then we cannot distinguish that.
Thank you.
Thanks.
Okay, so I have one question myself. So my question really concerns this old idea from Ashcroft. So it might be related to your research and it might not, and I apologize if it's not. So these materials usually sometimes described in terms of an effective spin gauge field. So for example, a ferromagnetic material. And what Ashcroft showed a few decades ago was that if you have some gauge field, this might stabilize the metallic phase in general, due to this non-trivial mapping that I don't want to go into right now, but I can show you the paper later. Do you find at all that in certain regimes that the presence of ferromagnetism stabilizes the metallic phase, or do you not see that at all? So basically, does the presence of ferromagnetism stabilize the Fermi liquid in some regime or not?
Great question. So first thing is where we observe the ferromagnetic phase, the resistance as a function of temperature shows an insulating behavior, for example, here. Mm-hmm. Now, resistance as a function of temperature, if this is showing insulating behavior, does not mean that the system is like a wood, right? It's not, I mean, it's not a perfect insulator. So there can be some microscopics. Now the problem is, when all these densities, the resistance as a function of temperature is showing insulating behavior. It's very low densities, but they are still showing integer and fractional quantum Hall effects as a function of magnetic field. So it's, for an experimentalist, it's very tricky to reconcile, because for an insulating system, I would not expect to see quantum Hall effect as a function of field. So this insulating, so you may ask, what's the meaning of this insulating phase? The answer would be, I don't know. It's we struggled a lot to understand that part, but there is yeah, we cannot really reconcile it. So again, just a couple of theories that came is one, if you have a transition from a metallic system to a Wigner solid, it cannot be a first order transition. So it needs to go through something intermediate phase. There need to be some intermediate phase, which is like a theoretical proof. So what again Professor Kivelson thinks is there is a microemulsion phase that kind of develops in this intermediate regime. And that microemulsion phase can have different domains. Some of them can be metallic, and that part can be responsible for showing the fractional quantum Hall effect. Now, also the spin polarization transition in that case also occurs in that microemulsion phase. But I did not go too detailed into that in the talk because again, just from the experimental data, I cannot tell it's a microemulsion phase or not. Now, one counter argument of that. So I just told you that the microemulsion phase, the metallic part of that phase can be responsible for the fractional quantum Hall effect. Now, what happens at very low densities, so 1.7, where we see a strong nonlinearity in differential resistance. So we think there is a Wigner solid phase at zero field, right? Now, even if you have a Wigner solid at zero field, you have integer and fractional quantum Hall effect at high magnetic field, which again seems kind of counterintuitive. But indeed, there are theories by Professor Jain's group that it all kind of boils down to how much Landau level mixing you have in the system. So at these fillings, say integer fillings or fractional fillings, such as 1/3, a fractional quantum Hall effect or the integer quantum Hall effect is more energetically favored than the Wigner solid, even if you go to large, very large Landau level mixing, even beyond our case. But if you come to zero field or the flanks between the quantum Hall states, Wigner solid is favored. So overall, the phenomena in this case is kind of complicated, but again, we kind of understand the presence of, say, Wigner solid or the quantum Hall states in down to low densities, and also the spin transition or the valley transition is relatively simpler because it happens in a metallic system, but also the spin transition. Now, the puzzle that we have is, I would say, has come up with the question that what happens to the very low densities? What happens to the magnetic property? But again, to our best effort, we can tell it's ferromagnetic, unless we can really measure the magnetic moment, which at this density is very hard. Yeah, I maybe to give a very long answer, but yeah, and we have, I would say, no clear signature of any stabilization of the metallic phase or the microemulsion phase that's provided by the magnetism in the system.
Okay, thank you.
Thanks.
So if not on any more questions, maybe let's thank Shafayat again.
Thank you.
Thank you.